No, it's just a dark percent.
It was on that page.
Barely.
Okay.
Wait, we using that calculator, right?
No,
Wait.
you're not gonna need it right now.
Well, we don't need to
You'll need it when you start working on the assignments that I give you.
The one. Let her talk.
No, I'm just wondering why I started the video and we're still talking and. Okay. Section 6.2 is on complete graphs. Okay, I told you yesterday, we are going to start learning some formulas today. Okay, I will give you these formulas for your test on chapter 6. However, these formulas will not be given to you for your final. Okay, you get a formula sheet for your final, but it's all on arithmetic and geometric sequences. That's all you get. Okay, so a complete graph is a graph in which every pair of distinct vertices is joined by exactly one edge. So there is only one line that connects any dot to another dot. Okay. They call it K. That stands for complete graph. And then they'll make it a sub of a number. So this graph right here is K sub 3. The K stands for the fact that it is a complete graph. The 3 stands for the fact that it has 3 vertices. I know, they ask me all the time, why don't they use C?
Exactly.
Next one is K4.
Okay, so this next one is K4 and K5.
The ones in the middle doesn't count because they're already connected by the ones on the outside.
So, use the definition of a complete graph to answer the following question. Does a complete graph have to be connected?
Yes.
Absolutely. Is a complete graph allowed to have loops?
Yes.
No.
No. Okay. Remember, it says every pair of distinct vertices has exactly one edge. So that means you have to have 2 separate dots and an edge in between. You cannot have an edge that goes back to a dot. So if it is a complete graph, it must have absolutely no loops. Can a complete graph have multiple edges?
Yes.
No.
Yes.
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 No.
It's yes.
Look at that, just kidding.
Oh my god.
Oh my goodness.
Oh,
Exactly 1. There can only ever be one line that connects 2 points.
no. That is fake.
Huh? There's still no multiple edges in it. Remember, a multiple edge would be like if I did this. And there's 2 lines that connect 2 dots. So you can have more than one line coming out of a dot, but you can't have more than one line coming out of a dot and going to a same dot. Okay? So, no, they are also not allowed to have multiple edges. Can the different vertices have different degrees?
Yes.
So, before we can do this, we need to take a look. In K sub 3, what's the degree of this vertex? What's the degree of this vertex? They're all 2. Take a look at K sub 4. They're all 3. Over here, they're all 4. So no, they cannot have different degrees. They all must be the same. What else do you notice between how many vertices you have and the degree of each vertex?
Exactly the same.
K sub 3 has a degree of 2. It's 1 less. Okay, it's 1 less. So there's your first formula. Okay. So the degree is equal to the number of vertices minus 1. Your degree will always be 1 less than the number of vertices that you have. So if I tell you that you have a graph, K sub 10, each vertex should have a degree of 9. Okay?
What's the catch?
It's going on.
There's not really a catch.
It's on.
I mean, I don't know what you want me to say to that. It's not really a catch, friend. Hold on. Okay, so if I have K sub 3, what's the degree of each vertex?
2.
If I have K sub 4, what's the degree of each vertex?
3.
K sub 5 would have a degree of? K sub 6 would have a degree of? Okay? So now that you know this, what do you think the total degree of K sub 3 would be? 6.
Because there's 3 edges.
So you have 3 dots that each have a degree of 2. So 3 times 2 is 6. So I have 4 dots. Each have a degree of 3. 12. 5 dots. Each have a degree of 4.
5.
That's 20. 30.
And 30. So to get your total degree, we take the vertices times the degree. There's formula number 2.
You have enough. That's right.
She said she would.
Okay. There's also a formula for the number of edges that are in each graph.
That's very degree.
For the total degree? Yes. Okay, so let's go back to this. How many edges are in this picture? 3. How many edges are in this picture? 6. 1, 2, 3, 4, 5, 6. How many are in this picture?
10.
There are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, let me go back to here. So this has 3 edges, this has 6 edges, this has 10 edges. How many does a complete graph of 6 vertices have then?
20. 12.
Oh.
It's just half of it.
15!
It's just half of the
They go
total
over.
degrees.
It's half of your total degrees. So your edges are taking your total degree and cutting it in half. So your formula here is total degree divided by 2.
Numbers.
This formula you actually already knew. Let's go way back to chapter 1.
No.
Oh, yes. If I have 4 people
Divide by
in the
2.
pairwise comparisons, how many people do they have to face?
4, 3.
3. They play everybody but themselves. So the 4 people would represent how many vertices you have. The people that they face would be your degree divided by 2. So we're actually using the same formula that you learned in pairwise comparisons.
I'm dead.
So it's come back to haunt you
Connected. It's all connected somehow.
somehow, some way. Really.
Electrostructure.
Woo!
Boy.
Okay, so to summarize everything we just talked about, then we've got one more formula to come up with. To summarize, K sub n. N is how many vertices I have. If I know my number of vertices to get the degree, I take the vertices minus 1. So technically I would take n minus 1. Because again, N represents your vertices. To get your edges, you would take your vertices times your degree and divide it by, whoa. Go
By 2.
divide by 2. I don't know why that popped up like that. Do I?
Caleb Galloway.
Oh, everybody say, hey, Caleb. Maybe he's watching live. Is he watching live?
He better comment. Yes.
Oh, he said, hey, Miss Smith.
Hey, Caleb.
And then he said 5. Hey. He's talking to us. Peter.
Probably at home when his parents are like, who's that crazy girl yelling at that?
Right. Why are they calling you Peter? All right. Here's the last piece. In a complete graph, you will be able to tell me how many distinct Hamilton circuits you have using a formula. Okay, so take a look at my complete graph of 3 vertices. How many Hamilton circuits
2.
start and end at A?
2.
2. You've got A, B, C, A, or A, C, B, A. 2. Remember, Hamilton says you start at A, you go to every vertex, and you go back home. Let's find all of your Hamilton circuits with 4 vertices.
3.
No, there's more than 3. A, B. You
Go
said
with the
B.
simple. Go with the simple one.
Hold on. A, B, D, C, A. I can reverse it. A, C, D, B, A.
Now go complex.
Now do what?
Complex. So A, B, C, D, A.
A, B, C, D, A.
Go reverse.
A, D, C, B, A.
That's it.
A, C, what, Dewan?
A.
A, C, B, D, A.
So isn't there a reverse for that?
And A, D, B, C, A. So there are a total of 6. Okay, so K sub 3 has 2. K sub 4 has 6. If I flip the screen, K sub 5 has 24. K sub 6 has 120.
Can you
So
go
we're not
back?
getting the
You
right?
flipped it too quick.
I flipped it too quick. I'm sorry.
Is this gonna be like the
Thank
other
you.
one?
The what?
The other one.
What do you mean the other one?
Whatever, like, you remember. One 5 and 1.
You don't know what he talking about when he had the when it was.
She didn't put that on my test. I thought it was. But anyway, yeah.
About the Schubert,
Shapley Shubik.
Schubert,
Yeah.
Schubik, and then the other one, the first one.
It's one of those formulas from chapter 2. It's one of the formulas we learned in chapter 2.
It's the beautiful.
Do you remember which formula?
The 2n minus 1.
No, it's not the 2 to the n minus 1. What was the other formula we learned in chapter 2? Huh? No, Bonshoff was the 2 to the n minus 1. So you were on the right track with Shapley. But what did I use to find the amount of sequential coalitions?
Oh, you go in order. So 3 times 2 times 1. Yeah, right?
Which was what in math?
Wait, I don't know.
How do I write
Oh,
3 times 2 times 1?
3
What?
question mark. 3
I was thinking of question.
3 question mark.
Exclamation point.
Oh,
Okay, so to get the total number of distinct Hamilton circuits, we take the degree of each vertex and I factorialize it. Because 2 factorial is 2 times 1, 2. 3 factorial is 3 times 2 times 1, 6. 4 times 3 times 2 times 1.
Like 80.
24. 5, 4, 3, 2, and 1.
It's 55.
It's
That's not
1.
the point anyways.
20.
I have a question. When we did this on the test, are we gonna have to do it like strictly so we can show our the method we did it? So on the test for chapter 2, we had to do
No.
5 times 4 times,
So, no.
or can we just do 5 question mark?
You would be able to just do 5 exclamation point.
Okay.
If you put 5 question mark, I'm marking it wrong. That's not a question mark. I'm not lying. I'm bluffing.
Told you.
On what you know about world?
So, distinct Hamilton circuits in K sub n. So, it's n minus 1 factorialized, or the degree of your vertex factorialized. That is your last one.
Ms. Smith,
Yes.
on what you will mark your own?
He wanted to know, like, if it was 5 factorial, do you need to write out 5 times 4 times 3 times 2 times 1? No. 5 factorial would be just perfect. I'm telling him though, if he writes 5 question mark, I'm marking it wrong.
On what?
Because it's not a question mark, it's an exclamation point. So,
Bluffing.
on
I'm flipping it.
that minus 1. Okay, so what you need to be able to accomplish with these formulas is I should be able to give you this. And you should be able to tell me how many vertices you have, the degree of each vertex, the total degree, the number of edges, and the Hamilton circuits.
Are we ever gonna have one?
No, we better not. Don't listen.
Okay, so if I have K sub 24, how many dots do I have? 24. This number goes here. If I have 24 vertices, each should have a degree of 23. My total degree, well, I have 24 dots, each with a degree of 23, so you would do 24 times 23, which would be what?
255.
Somebody with a calculator on your desk.
268.
Bro,
3.
24 times 23, oh my God.
I was playing snake on a calculator. It's
560. 578.
552.
552.
Okay. How many edges do I have then? Well, you take this and divide it by 2. So it's 2, 7, 6.
6. 576.
And your Hamilton circuits then would be 23
23.
factorial.
Okay, so for the
Exclamation
degrees,
mark,
always lower
question
than
mark,
actual.
Period.
No,
At the end.
1, always.
do not.
Right.
leave that out.
Question mark. and a Period.
Oh, I
At
did.
the end.
Leave that out there.
Okay. I should also
No.
be able to make you work backwards.
Oh.
Wow.
You good, homie?
Wait, as long as you give us the Hamilton circuit, then I think we could do that.
So, I should be able to tell you that you have, hold on.
She thought about it.
Actually, you can really.
I should be able to tell you your Hamilton circuits are 720, and you should be able to work backwards.
That means our K is gonna be 721.
Can't you do the same with the
No.
number of edges?
No,
See, she doing it anyway.
no,
Yeah.
no, don't listen to him.
You can
Crazy.
You just
Crazy
multiply.
talk.
You said crazy talk.
So, the way you would work it backwards,
You have to give us
the
something.
way you work it backwards with Hamilton circuits, okay, you do the opposite. So normally, you start at the higher number and you multiply down. So now we start with the lower number and divide. So if I divide this by 1, is it going to change it?
No.
No. But I can divide it by 2. What does that give me?
Number. It's like 400 something, 300 something. 366.
360. Then I divide by 3. What does that give me?
120.
120. Divided by 4 gives me 30. Divided by 5 gives me 6. So this now tells me that I have a degree of 6.
So you simplify.
So if I divide starting at the smaller number, it gives me how many degrees I have. The degree then will tell me my vertices are 7, because it should be 1 higher. My total degrees then is 7 times 6, which is 42. And my number of edges then is 42 divided by 2, which is 21.
I'm sorry, how did you?
I'm just, okay,
I'm
so.
confused at the bottom part with the Hamilton, circuits, how you do it.
You
Well-
have to start at the smaller number. To work forward with Hamilton circuit, you start at the bigger number and you multiply down. So you need to work in reverse. So you start at the smaller number and divide backwards.
Upwards.
So-
It's not really backwards.
So basically this week doing Hamilton circuit started to.
So, hold on.
Alright, I'm just.
So, 6 times 1, which is 720.
Oh, okay.
So if I give you this, we go backwards. 720, and instead of multiplying, I'm now going to divide. Well, if I divide by 1, it's not going to change it. So we start with dividing by 2, and that gave me 360. Then I divide by 3. That gives me 120. Then I divide by 4. That gives me 30. Divide by 5. That gives me 6. So 6 then tells me how many degrees I have. And then I can work from there and get my vertices, my total degree, my number of edges. You're fine. This is what I'm here for you to be like, stop, explain that again.
But how do you know you're gonna start at that? Just write the big number. Like, how do you know how many it is? Or will it
So-
tell us?
I will always give you this, the
Okay.
big number. You know to stop when these are 1 space apart.
Okay, okay.
So, for instance, let me, because I know there's a problem with this on here. Let's look at, if you flip the page where the independent practice is, let's do this one. This is number 11, part A. You're fine. So, it tells you that you start with 5,040 Hamilton circuits.
Just add 1.
Why?
Ma'am,
Yes, ma'am.
did you check your email?
Yes, ma'am.
All you have to do is add 1, so it'd be 5041. And then
Add 1 to what?
two-
Why are you adding 1?
You
Because that's not your degree. That's how many Hamilton circuits you have.
Exactly. Why are you yelling? Because the Hamilton circuit is always just 1 away from the actual K thing. It's always been 1 away. So if you give us the Hamilton circuit, you just add 1 and then you get your K24.
You don't have the number. You don't
So
need
you
the
divide.
Yes, I know. But she gave us the Hamilton this so we just all you're gonna do is gonna be 41 and then that's your K and then from there you can just work from the top all the way down. Yeah.
That's not your degree of each vertex.
Homie.
What? What are you talking about?
Homie. Homie, what?
I'm not saying anything about any degrees.
It's-
Homie, what do you prefer?
How we doing that at work? It just-
You are so confused. What do you mean? Okay, explain what I mean. I'm not understanding.
I'm not understanding either where you're
Yeah.
adding one to that. Why are you adding one to that?
Good.
Cause it's always just been,
But you don't
one
have,
away.
she's not giving you your.
Yes, I know.
You were looking for that.
I know.
So what are you adding?
I already got it though. If you add one to the Hamilton, distinct thing, if you add one to this, you get this.
No, you don't.
Yeah, you do.
No, you
Cause it's
don't.
always been one.
No, you don't.
That's your verse, Tony.
That's how many dots you have in your picture.
It's been the, what you call it, K on top, right?
I don't know what he's talking about.
The K, whatever, the K dot,
The K.
Uh-huh.
it's always been one away from the Hamilton.
No, it hasn't.
Yes, it has. The
No, it
Hamilton circus is one that's multiplied 3, 4, 5, 6, and on up.
What the hell you doing?
Are you talking about?
I'm
Oh,
not,
cause he got, the
I'm not
23
telling you what
actually-
number is factorialized.
Yeah, that's what he-
I'm telling you the answer of this.
Yeah.
So I'm not telling you that 720 is 6 factorial.
Wait, why'd you go that way? What?
Bruh. That's what we got.
No,
I'm confused.
Rodrigo?
Never mind, go ahead, go ahead.
he's hurting my head. Give me a second and Dewan and I will try to get through to you.
No, it's okay.
Because you're taking this way too, okay.
He just
All
right.
too far.
So we start this process again, dividing by the smallest number. So I don't want to divide by 1, it's not going to change anything. So we divide by 2. This takes me to 2520. Then we divide by 3. Somebody's going to have to do that for me.
840.
Thank you. 840 divided by 4.
210.
210 divided by 5. You said 42?
10.5. It goes into it. Oh, never mind. I messed up.
42 divided by 6,
7.
and you get 7. So Alicia's question was, when do I know I stop? Okay, I divided by 6, and I got a number that is right above it.
8.
So this is my degree then. So my Hamilton circuits are 7 factorial. Now, Rodrigo, you can add 1.
What are you talking about?
When I have this in 7 factorial,
That's when I wanted.
then you can add 1 to get your vertices. So this means I have 8 vertices. They have a degree of 7. My total vertices then are 8 times 7, which is,
56.
thank you.
That's simple, man.
And my edges are 56 divided by 2, which is 28.
28. Yeah. I missed first grade. What was that?
So, Rodrigo, before you add 1, you have to figure out what this is written like this. The factorial button. If you go to math and
I thought it
scroll
was
over to
six.
probability and choice number 4. Are we okay?
Yes.
Yeah.
Stay low.
Say bye, Caleb.
Oh,
Bye, Peter.
Another one.
it was fun. Y'all probably should. Smell it.
Caleb